Hei, Boris Martin, og velkommen til Tromsø og Midnattssolkonferansen. The Midnight Sun Conference is sponsored by SPKI, NSE, Visual Intelligence, Helse Nord, UiT, Norwegian Nuclear Medicine Consortium, Health Data Lab, and UiT Machine Learning Group. My name is Kajsa Møllersen, and I will be your MC, guiding you through the program, presenting the presenters, taking questions, and providing all necessary information. This conference is bilingual. Some sessions are in English and some are in Norwegian, and I will be switching between the two as we go along. It is bilingual in another sense as well, with participants from two different fields, healthcare and technology. Myself, I have a PhD in statistics, but common for all participants here today is a foot in each field, regardless of educational background. Presenters and participants are gathered here in Tromsø and also scattered around in different locations, brought together by the screen behind me. For digital coffee breaks, there is a virtual room where you can participate with an avatar. Link and information is provided on the conference website. In addition, we will be using Twitter and the hashtag MidnightSunConference. And Twitter has proven to be quite a lively discussion forum on many conferences the last year. So don't miss out on that. All talks are broadcasted, and after each presentation, we open up for questions. But raising your hand will take you nowhere. Instead, you have to write your question in Slido, and I will direct the questions to the presenter if there is time. Because since this is a hybrid conference, I will be very strict on the time schedule, and all presentations will start exactly as announced in the program. By this, we hope to smoothen out the difference between physical and digital participation. But there is one large distinction still. That is the COVID restrictions for those participants present here in Tromsø. And pay close attention now, because I will only say this once. You all have designated seats. Please don't switch seats, because then we would need to disinfect, and we simply don't have time for that. A lot of you, especially the crowd from healthcare, are already vaccinated, but many of us, including me, are not. So we all need to keep the 1 meter distance at all times, even if you are fully vaccinated. Coffee will be served just outside, and there are several coffee stations, all equipped with antibac. There's a long tradition in Norway to mix coffee and alcohol, karsk it's called, but this time the alcohol is for the hands. Bathrooms are situated both to the right and the left, just outside. Avoid crowding and wash your hands. In case of an emergency, there are plenty of doctors present here today, both medical and otherwise. But if the fire alarm sounds and we need to evacuate, the curtains here will draw back and the emergency exits will appear. Walk out and to your right and follow instructions from the hotel staff. If you have COVID symptoms, go home, make an avatar, and follow the rest of the conference digitally. Finally, if you comply to all these rules, the lunch will be served in the restaurant at 12:10. So, now I hope that you are all comfortably seated here in Tromsø or back home, wherever you are, and ready for a short opening speech by Maria Jarman Bjerke from the Ministry of Health and Care Services.
Kjære alle sammen. Først av alt vil jeg si tusen takk for at jeg får lov til å åpne denne spennende konferansen. Regjeringens mål jo å skape pasientens helsetjeneste. Og derfor jeg veldig glad for at denne konferansen handler nettopp om pasientnær kunstig intelligens. I Nasjonal helse- og sykehusplan har vi vært tydelige på at bruk av teknologi i helse- og omsorgstjenesten ikke et mål i seg selv. Verdien ligger egentlig i hva det kan bety for pasienter og helsepersonell. Med kunstig intelligens så kan vi bedre nyttiggjøre oss den stadig økende mengden informasjon som vi har tilgjengelig. Slik kan vi få bedre helse- og omsorgstjenester, vi kan gi et bedre grunnlag for forskning og innovasjon, og mer effektiv ressursbruk. Pasientene kan få mer persontilpasset behandling, men lavere risiko, og forhåpentligvis færre bieffekter. Helsepersonell kan få bedre beslutningsstøtte, og vi kan også bidra til å øke pasientsikkerheten. Bruk av kunstig intelligens det betyr at noen oppgaver som hittil har vært forbeholdt mennesker, de kan gjøres bedre, raskere og rimeligere av maskiner. I tillegg så kan ressursene som i dag brukes på behandlinger med liten effekt, brukes på behandling som har effekt. Bruk av kunstig intelligens i helse- og omsorgstjenesten, det skal være trygt og forsvarlig. Ansvaret ved bruk av slik teknologi, det må være avklart, og etiske dilemmaer må kontinuerlig vurderes. Innbyggerne må være trygge på at både personvern og informasjonssikkerhet godt ivaretatt. Derfor må nasjonale rammebetingelser tilpasses for å kunne ta i bruk kunstig intelligens på en trygg måte. Regjeringen har lagt frem en nasjonal strategi for kunstig intelligens som omhandler grunnleggende forutsetninger for å kunne utvikle og ta i bruk kunstig intelligens, hvordan Norge skal utvikle kompetanse innenfor dette området, og hvordan offentlig og privat sektor skal kunne utnytte den innovasjonskraften som ligger i kunstig intelligens innenfor etiske rammer. Så også kunstig intelligens en stor satsning i EUs nye langtidsbudsjett. Regjeringen har besluttet at Norge skal delta i EU-programmene Horisont Europa, Digital og EU for Health. Det åpner for store muligheter for finansiering av KI-relaterte prosjekter for norske forskningsmiljø og næringsliv, og muligheten til å ta del i spennende samarbeidskonstellasjoner med europeiske kolleger. Vi har også fremmet et forslag for Stortinget nå om endringer i helsepersonelloven som ligger til behandling nå. Forslaget åpner for bruk av kunstig intelligens i utvikling og bruk av kliniske beslutningsverktøy. Vi mener at taushetsplikt ikke skal stå i veien for at viktige beslutningsstøtteverktøy kan utvikles og tas i bruk. Helsedirektoratet i samarbeid med Direktoratet for e-helse og Statens legemiddelverk utreder nå mulighetene og utfordringer med å ta i bruk kunstig intelligens i pasientbehandling. Og dette krever at vi ser alle virkemidlene våre i sammenheng, slik at de trekker i samme retning. Og jeg ser av programmet at Helsedirektoratet skal orientere nærmere om dette arbeidet i morgen. Så det skjer altså veldig mye på dette feltet. Jeg håper dere alle sammen får en veldig spennende konferanse. Lykke til videre, og tusen takk for oppmerksomheten.
Welcome to this first session, which will be in English. It's named AI-derived risk stratification using EHRs, registry data, and other non-imaging data. All speakers will participate virtually, and remember to use Slido to ask questions. First speaker out is Bart Gertz. He's an anesthetist, intensive care physician, and clinical pharmacologist from Amsterdam, with an interest in perioperative process optimization. 3 years ago, Bart started Health Plus AI, which has been involved in several projects here in Tromsø. And he will be sharing some of his experience with this company. Change in program. So we will instead introduce Kasper Jensen. He is passionate about driving change in both the public and private healthcare through IT architecture. He's been working with digitalization, healthcare, and natural language processing for decades, including 2 years at the Norwegian Center for e-Health Research here in Tromsø. The topic of his talk is one of his key interests and main research focuses, which is text analysis in health records.
Hello, good morning, everyone. Just give me 1 second. I'll share my slides. Are my slides showing on the screen? Can I start? Yes. Okay. Well, thank you and good morning. My name's Kasper, and I'm a solution architect in IQVIA, which is a company that is working with a lot with healthcare and innovation in the healthcare sector. So in this presentation, I'm gonna give a brief overview and introduction to one of my key research areas, which is analysis of free text in health records. But first, I just want to give a really brief introduction to what IQVIA is and why we are working with this and why it's so exciting for us. Because so IQVIA is driven by that it's a company that is focused on creating a new value and accelerate results in healthcare to improve the general health of people and by using technology. And IQVIA is a global organization that with a lot of different healthcare experts and technology experts that are together working in order to bring new technologies to help patients and clinicians in their daily work. And one of our main strengths is that we have a very big focus and around how working with improving patient outcomes. So this is really short about IQVIA. So IQVIA is a company. We are in more than 100 countries and have existed for 60 plus years. It's a company with more than 1,800 PhDs, more than 1,300 medical doctors worldwide, and in total is we are around 70,000 plus employees today, located everywhere in the world. What is the current state as we see it in healthcare, and why free text and working with information from free text is so important is that we see that there are some really unique challenges in the healthcare sector and industry today, and one of those is that we see that we have some cases where we see that we have 5% of the patients in some countries. They account for almost half of all medical costs. And we also see that there is people, they live longer and and they become older. And as the population is aging and the cost of treatment of patients, they are increasing. We see that there is a big need to bring technology to help us manage the healthcare and the way that we do treatments to improve that, so we can get better healthcare for everyone. So basically, when we're looking at the
Sorry, Kasper, we cannot hear you anymore. Maybe you have lost your microphone or something.
Yes, is it better now?
Yes, thank you.
Okay. So what we see is that governments around the world, they sit on a wealth of information, but on health data, but this is often unstructured, siloed, and inaccessible due to regulatory constraints, or the data not being standardized due to different clinical codings. That makes it expensive to manipulate and run analytics on healthcare data. And all of this, this makes also the whole roadmap towards having a data-driven decision-making in healthcare. It makes that roadmap difficult because we need to manage those obstacles on the way there. So one of the things we're working with is that we work with the governments that helping them that they must leverage, or how to leverage the data and technology in order to manage and analyze healthcare data in a low cost and efficient way, so that we can get better healthcare. And one of the issues that we see in such a journey is that one thing is data usually is lacking agreed representation and formats, so that they can be reused for the projects that we want to use them for. So usually one important aspect about using healthcare data is to have standards or data standards for how is data actually looking like, and how is it to be structured and used. Then other things we see usually is data privacy issues or concerns, where we have to keep in mind that when we are working with healthcare data, we are working with data on people. And we have a special job here to protect that data, and this provides again some limitation or challenges, or that where we have to work with data in a way that we are always keeping data privacy in mind. Another thing that we see is that we have so another issue in healthcare is data interoperability, where it's for many in many situations it can be difficult to actually access data from in the systems where they are available, and use that to drive a project on clinical decision making. So so one thing is, in addition to the privacy challenges around managing the privacy around it, we actually also see another challenge, which is the interoperability. So the ability to actually physically access the data, which is also sometimes giving some challenges that makes the road towards data-driven decision making difficult. So another issue or challenge that we see is that a lot of the data is actually unstructured data, and we lack tools in many cases to easily manage and make use of this unstructured data. And that requires concepts that we need to work with, such as text parsing, analytics of text, taxonomy, and metadata management, which are new disciplines that require special tools to work with such data. So, and then there is we see other challenges as well, such as actually where is the data to actually physically placed, which is typically also an issue that we have to think about when we're working with healthcare data. And this is usually a discussion about, can we use cloud solutions when we're working with healthcare data, or does it have to be on-premise on some machines locally? And these questions can usually be really big questions, especially when we're working with healthcare data. So these are some of the other challenges that we need to manage when we are working towards enabling data-driven decision-making in healthcare. Then there is a lot of other things. Actually, there is also challenges such as how do we actually federate data and join data sources and provides consolidated views across different data sources and systems, where we see a situation where there are actually a lot of healthcare data available, but usually they are scattered throughout multiple different systems. That makes it difficult to get a one view of the patient. So that's also an area where we are focusing a lot, and we need to have focus on to enable data-driven healthcare. And then there is the need of having real-time access to data, which actually requires new standards for many of the systems that we have today, and that we are going to use in the future. And then there is the question about, or the main thing is that when we have enabled all this, then we have the issue of, or the part where we actually, on top of the data, are building some predictive models using AI and machine learning. And here we also see a multitude of challenges. So that one thing is we need to ensure that we have a good quality, that we have infrastructure to actually run these kind of algorithms so that they can be used in a clinic or by the patient. So the infrastructure in order to actually realize these methods is also of great importance and something we focused on. But then so that's basically some high level of how we see the different challenges in healthcare today, and the different challenges that we need to work on and that we are focusing on in order to help drive healthcare forward and give better products and tools to both patients and clinicians. But there are some challenges on the road there. So basically, usually when we are working with healthcare data, we have typically 3 different source systems that we are focusing on and are getting data from. And one of these source systems is the electronic medical records, which is one of the main records that you're using at the hospital. And but there are also other data sources that are extremely interesting and relevant. One is the information about prescription medicine that you usually need to see the context of the treatment that was given. And there is also a third data source that is extremely interesting, and that is the electronic care journal. So one thing is we have a medical record at the hospital, but then when the patient leaves the hospital, at least in Denmark, we actually have separate systems for for that we call the electronic care journal. So it's its own journal system, which is to some extent has a similar nature as the medical record, but it's more focused towards the home care part of the patient. So in order to being able to follow a patient from start to end treatment through the healthcare life cycle, that involves actually not only looking at the medical records, but it also involves looking at what is going on outside of the hospital and the records that we are keeping locally in the municipalities where people they get out of hospital care treatments. And then again, this data is I think one of the main challenges in using such data, that is that it's not easily accessible and usable. And so when we are extracting this in kind of information, we always need to take into consideration that we need to apply proper anonymization. So that people's privacy can be preserved, but we also will be facing integration issues where we need to integrate different systems with and the different components here, the different sources. They need to integrate towards the machine learning method that we are building and the way that we are showing dashboards and visualizing data. So that's also that's some of the things we need to do in order to get to a data-driven decision making. And then usually this data also we have to apply normalization to this data to make it meaningful. And sometimes we have to enrich with other data types, and all this data needs to be managed and visualized, which actually makes it several steps before we can take source data and apply it in a decision-making context. So that was a quick introduction. So in this study that I did, we studied a population from the electronic healthcare records from a university hospital in northern Norway, and basically the reason that we did this study is that we see an aging population and we see an increasing complexity in patients' disease trajectories, where physicians are often met with complex patient histories where clinical decisions they must be made. So with an increasing rate of adverse events and hospitals facing financial penalties for readmission, we see that there has never been a greater need to enforce evidence-based data-driven decision making using the available data that we have in the systems where they are. So in this present study here, we followed a cohort of around 7,700 patients, of whom 4,000 patients were diagnosed with cancer and surgically treated at the university hospital in the years 2004 to 12. And in this study here, we proposed a methodology that allows disease trajectories of cancer patients to be forecasted based on the data that you can find that you have available in free text in the electronic health records. And we show how disease trajectories can be used to make such predictions and in which context. And so basically, before we could actually start such a study, first we needed to manage the data privacy part. So we got an approval from the Data Inspectorate and Ethics Committee to use the data for this particular study. And then we identified the cohort that we wanted to include in this study, so the patients that we wanted to follow in this study. And then we went into the medical record system and identified the medical records for this cohort of patients. So that is some of the manual work that we did in order to get some initial data to perform this study. Then we extracted the information from the records for these 7,700 patients, and we got their free text journals. And basically the records they include different elements from patient journals. That could also be an admission journal or nurse notes or doctor notes, but they include different types of records that we used for this study. So when we're saying medical record, we're not talking about just a very specific type of data, but it's actually a multitude of different types of notes and journals. And so in total, we had around 1,133,000 unstructured text records that we then could extract for these 7,700 patients. And many of these records were from the intensive care unit. So this is to give a brief introduction to what type of patients did we study here, and what is it that we can do with this data that we have on the patients and why it's relevant. So using free text data, it's I think this is not anywhere easy to actually do that if it's to be done by a machine, because machines they read information and process information very different from humans. So the first thing we had to do in order to use this data for our study, that is, we had to conceptualize the information. So that means that the first thing we needed to do in order for this data to be used by a machine is we needed to convert the text that was handwritten, or it was written on a machine, but it's written by humans. Convert that into concepts that a machine can understand. And the way we did that is that we had to match the writing in the records themselves to known terminologies in the Norwegian version of MESH. So MESH is an international ontology of medical subjects, and we use this as a way to create a link between what has been written and what the meaning was of what was written in the journal. So one of the challenges in doing that is that the human writing comes with a degree of variability. So, and especially when you're writing fast, there will be spelling mistakes. There will also be variations in how you spell things. And that makes it difficult for a machine to understand what is actually being written in the document, because what the machine has to do in order to make it context out of what is written, it needs to identify that in an anthology, and the anthology here, that's the Norwegian version of MESH. So in order to do that, we applied an algorithm called Swift-Morterman, which allows the machine to match terms what's written in the text with the Norwegian version of MESH, allowing flexibility in how the writing was done. So this helps the machine identify, create a link between what is written in the journal.
Sorry, Casper, you're a bit over time, so you would have to wrap it up in a minute.
Oh, okay. Yeah, sure. Yeah, so basically we converted the text, and then we trained some different classifiers to place the different concepts that were extracted in how they were written in the journal. So if it's something that happened now, or something that happened in the past, or if it was internal information, so we can distinguish that in the records. And this helps us actually build for the machine a context to understand these words. And to do that, we built language features. So the machine needs to be trained in what kind of features is it that it needs to use in order to perform this classification. And then after doing that, getting the things into context, we built trajectories, and we did that by handling comorbidities where diseases where a patient can have multiple diseases at the same time. We need to build trajectories that supports that. So here we used frequency mining to enable trajectories to be created, and that allows us to group what events the patient is experiencing over time on a kind of a linear scale. And this slide here just shows how does this actually perform, and what we show here is that creating these trajectories performs quite well actually in predicting upcoming events for this group of patients, and we see quite high ability to actually predict such events, where we also really have a really good option of managing noise and randomness, so that we are sure that our trajectories, they are not explaining events that are that could have occurred by random. So we needed a way to separate the randomness of a patient's journey with what do we actually know as causal events. And this is so this slide here is it shows that how we are managing confounders. So when working with this kind of data, it's heavily confounded. So here we developed an approach to actually manage the confounding factors, so that we can get good estimations on the trajectories. And so here what we see here is actually just it's a high-level summary of some of the many symptoms and disease events, and how we see that correlate to different cancer diagnostics, where we see what is the risk of when you have a certain event, what are the risks then of being diagnosed with cancer later on. And we show here what is the risk then when we are doing when we are managing confounding and factors. Oh, that was it.
Thank you very much, Kasper. I have a question for you from Slido. So in your experience, what is the most difficult challenge in doing analysis with Norwegian clinical text?
So the most difficult thing, I think, if you're looking at Norwegian text, I think the most difficult thing is to create the conceptual information. So basically, this slide here on slide 8, this is once you have completed the conceptualization of the information, then you are on a good you're at a good place. But converting Norwegian medical writing, what a doctor or nurse writes in a record, converting that to concepts that a machine can understand, that I think this is the hardest challenge when we're looking at Norwegian text. But I think this doesn't only apply to Norwegian; it applies to many other countries. I think if it was Danish or Swedish, it would it would be the same challenges. But I think this is probably the most difficult part when it comes to the language itself.
Thank you. Thanks to Kasper. We will be moving on in the program, and now a second speaker out, Bart Gertz, the anesthetist, intensive care physician, and clinical pharmacologist from Amsterdam, who 3 years ago started this company called Health Plus AI, and he is here to share some of his experience with this company. Bart, please.
I'm just gonna say hi to everyone from afar. Hi from Amsterdam. Sorry for messing up the program slightly by getting the time wrong, but happy to be here. And also, just to be very Dutch again, I'm gonna actually talk a bit more about a piece of applied AI, a project that we finished before, basically as my last job at the Amsterdam University Medical Center. So I'm happy to do that. See if I can get this working. There we go. I hope you're now seeing my display. Yeah.
Yes.
There we go. There's a slight lag time, I see. It's good to have some idea of what's going on in Tromsø. Yeah, so my background is anesthesia, intensive care, clinical pharmacology. I'm going to focus on the first two specialties, on a very practical problem, if you want, and also looking at the previous presentation, add one source of data that's a bit closer to the patient, as in physically. Just to disclaim my conflict of interest, the project that I'm going to talk about predominantly is sponsored and was a joint project with Edwards Life Sciences, a major US listed medical device company, and my other conflicts of interest are listed here. So I'm going to dive right into the medical problem. If you, and I know that most people in the audience are not physicians or nurses, so please do interrupt if I'm not clear enough. So low blood pressure or hypotension is something that we see a lot in the operating room and in the intensive care unit. And we know from medical literature, major database research of 100,000 to 200,000 patients, that the occurrence of even 1 minute of low blood pressure, being a mean arterial blood pressure below 65 millimeters of mercury, can lead to a significant increase in the risk of all kinds of nasty events happening to the patient. So like an 8-fold increase of myocardial infarction, so a heart attack. And this really shows up to the level where there's an association with mortality right after surgery. So I think this is a significant risk, and historically we've been looking at this problem quite a lot, but the treatment is pretty much reactive. So if you look at how many times do we see this issue, that's actually also very significant. And I'll dive into some examples in our own clinic shortly. But this also shows in the ICU, the previous images related to operating room data, and also shows for our intensive care patients that there's a clear correlation between the occurrence of low blood pressure and, in this case, acute kidney injury. We looked at low blood pressure in a more sophisticated way, not just in does it occur, but also looking at how deep is the event. And one can imagine that if the blood pressure is even lower, that will add to the risk for the patient. But also there's a mix of depth of low blood pressure, but also the duration. So this is really what we wanted to capture. diving right into the machine learning part, if you look at the arterial blood pressure wave, and this is something that might be close to home for a lot of people, as this is something you will get into biology classes in high school, you have a systole, contraction of the heart, and a diastole where the heart relaxes and blood is pushed through the major circulation of the body. Now, there's a lot of physiological research in the background, and of course, we didn't want that to go unused. But the premise that we set out on is, can we change the way we treat patients from reacting to a low blood pressure situation to predicting it using the same signal that we use to diagnose it? So really simple. That's going back to a different kind of source of data. We store these kinds of values about one value every minute when someone's in the operating room or in the ICU, and this is actually looking at a 140 hertz signal. So a pretty very highly granular depiction of what's going on with the blood pressure of that patient. We know of about 3,000 features or physiological measures from all the research that's been done in the past on pigs, on other animals, and on humans. I maybe know like 140 of these at most, but if we go to literature, there's about 3,000. And this is where the machine learning, the mathematical part starts, of course. Featurizing the signal, looking at things that we probably don't know or relations that might be there. We went to second line derivatives of all these known factors. This means that from every beat, every heartbeat, every blood pressure cycle, we now get 2.6 million features from this one well, less than a second, basically. And of course, looking at the data that we had with over 1,000 patients in total, some public data, some proprietary or our own data, but also data from our partners in the US. We separated the database into a training set of about 300 patients, cross-validation set, and a test set rather, and an internal validation set. But then again, you have hours of recordings, meaning that you have billions and billions of features to look at in total. And then this is, of course, also alluded to in the previous presentation. There's a lot of annotation that needs to be done that's not in the data. So we linked it to the electronic health record to see what interventions were done, when did actual hypotension occur, and all those things had to be done. So it's pretty intensive and a lot of manual work. And ultimately, we end up doing an external validation, and I will show the results of the clinical validation. So what I want to focus on is really how do you validate and bring this to the clinical practice. Looking at the internal validation, which is the upper three graphs, you could see that what we're currently doing is looking at the blood pressure change over the last couple of minutes and then extrapolating it to the near future. So basically what we do in clinical practice today is flipping a coin, or not much better than that in terms of decision making. Do I need to do something? We're pretty poor, or actually pretty awful at predicting the future in terms of blood pressure. And this shows the reactive nature of what we're doing in clinical practice. We were very happy, of course, with the performance of the model on the data that we provided. And then that was brought forward, that model, a linear regression model, and that was used on an external data set, the one from University of California, Irvine. And we saw slightly decreased, but equally impressive performance, at least from my perspective as a clinician. And again, the change in blood pressure, delta map, mean arterial blood pressure, didn't do much in terms of predicting the near future. So again, showing how poor we are as clinicians. This is an old tweet by Eric Topol, one of the, I would say, dons of machine learning and healthcare, from the clinical side at least, saying that we have, and this is, I think, a tweet of like 1.5 years old, but even now today we see a lot of approved models moving to the clinical practice, but only a very few of them have clinical validation, as in prospective clinical validation that was done. So again, looking at the external validation, this is something that we did. The blood pressure measurements are performed invasively and very accurately. What we did, we actually used a device that was non-invasive, so basically stuck to the finger with a cuff, so slightly less accurate way of determining blood pressure. And we used to look at whether we could use the same model on that type of technology as well. And we found again that there was pretty good performance of that model on a slightly different signal. So again, and also important is that we showed the relation in what the model then predicted. Of course, we had to chuck off the percentage mark. So we were talking about a number from 0 to 100, and we called it Hypotension Predictor Index, or indicator, as it's now currently called under FDA approval. And we saw that there was a clear link between the HPI value and the actual occurrence of the event. And as more you move to 100, closer to the event probably as well, you see that there's a clear coincidence of the interval of the prediction and the actual occurrence of one. So I'll speed this up a bit. Again, this boiling it down, taking from the ROC curves the values, and I think this is something that's for clinicians really important also to take in the back of your mind when you're building a model. How are you going to use it? And this was done ad hoc in this case, but showing that PPV was actually quite dreadful, but the other values were actually quite good for clinical use. It shows how you can use this. If the alarm does not go, and this is the shortcut clinical abbreviation or takeaway, one can use it to be safe and sure that there's probably not going to be an hypotensive event. But when the alarm goes, you need to really closely look at the patient, evaluate whether you want to do anything, but because not all predictions, or actually half of them, if you look at it, are actually true. For me as a clinician and as an academic researcher, it was really quite nice to see from within 2.5 years from conception of the idea of using this approach to be more proactive in terms of blood pressure management, to actually see this value come to life with HPI showing up on the new monitor on the right side in red. This was really something that kind of made it come alive for me. This is the secondary screen, I think also very important with the Decide AI work group that I'm part of, thanks to the Oxford group. This shows how important it can be to have actually pay close attention to the dashboarding. It is one thing to predict an event, it's another to actually put in the right action and convince people to act upon it. And I think this was pretty nicely done, although there's quite a lot of numbers here to review. This screen comes up, secondary screen, pops up when the alarm goes, and it is up to the clinician to really evaluate. And it goes back to what doctors and nurses are trained for in medical school: preload, contractility, and afterload. Is there something wrong with the heart? Do we need to supplant volume? Is not enough blood going around? Or do we need to make the vessels squeeze a bit? So really going back to what we're trained for. I think that early alarm, together with syncing with the training that people previously had, makes a really good way of moving people to an action, or at least evaluating the patient in the right way. So then we did a trial. It did end up in JAMA Networks, one of the better journals for clinicians or for clinical science. Not because it was such a big trial or a multi-center trial. We used 100 patients to basically look at whether we manage them the old way, the old-fashioned way, or with this tool, whether we could actually achieve lower numbers in terms of hypotension. So it was actually, I think, pretty un-JAMA worthy, but because it's one of the first prospective clinical trials, I think that's why it went into JAMA. We had a guidance, strictly speaking, not a protocol, in place, basically telling people, well, if this happens, you might, if the alarm goes, review the patient, and you can look at these things. Again, going back to the secondary screen. So there was no one pushing them to do an action. It's really up to the clinician, and that's, I think, important for this trial. So what did we see? Let's see, sorry. We saw that we reduced low blood pressure in terms of incidence, but also time-weighted average by 70%. So we saw a high number of events in the untreated, in the control group, and we saw that we could reduce it by 70% in the intervention group. We also checked whether this was safe. You're now predicting something, people putting actions into an event that hasn't happened. But we also showed that hypertension, the opposite of hypotension, did not happen in those same patients either. So there was no exposure to additional risk, because hypertension is not good for you either. But we did see a significant increase in the number of hypertensive events. We also saw that, and I think that's a really important part as well, we looked at how quickly people are intervening and also what they're doing. So there are smaller interventions done, and people are putting in quicker interventions. So it really shows that you build it up to the clinical endpoint. But then validation isn't done yet. It's all good and nice, prospective clinical trial. But the proof in the pudding is, of course, the eating. Do we actually see a reduction in the risks that we want to mitigate? Do we see a reduction in myocardial infarction, in kidney injury? And we don't know yet. So these were all OR trials, so we're also doing ICU trials at the moment, still connected to those. And there we see that the incidence of hypotensive event is actually 12%. So we're really average. We're not a perfect ICU at Amsterdam UMC. 12% of time people are spending in hypotension. And that number is actually slightly higher in the operating room. So it's good to also, again, iterate and see whether that problem is still existent, and it very much is. These are the first results in terms of accuracy in the intensive care unit, slightly better than the operating room, but that's not a hard fact. I deem that related to the fact that there's no surgeon meddling with the patient and doing things that are unpredictable, basically. Here you have patients and you have physiological and pathological mechanisms going on. Learnings, actually a lot or several. There are so many things where we can improve our way of managing patients. That's looking at curative care. I'm not even discussing preventive care, which I hope with COVID becomes more relevant. EHR data is very complex, alluded to by the previous speaker, but on device, on edge, machine learning is probably easiest. It also showed me that the innovation in healthcare is, of course, slow. On average, 17 years, 15 years before we actually get something from concept to the clinical practice. But this showed that within 2.5 to 3 years, you could actually get it running in now dozens, hundreds of hospitals across the globe within that time frame. Validation is very much related to the different steps and phases you have in pharma, and the regulation is picking up on that side. I hope it doesn't go overboard like it does with pharma in some aspects. So we get something that might be a very cheap solution or a cheaper solution and becomes more expensive. But it does show that we need to take these steps, not only to convince people, but to show that it's safe and that the interface and those steps also work. Also, there's a lot of discussion among my peers and a lot of people putting human versus machine, but I think it really shows that human plus machine work a lot better. And especially in radiology now, there's a lot of data coming out where it shows that it's just putting the benchmark a bit higher when they work together. And it's very much a team sport. A lot of data scientists don't know what the clinical practice looks like, what is relevant, and you really need to bring it together. Clinicians, patients, nurses, data scientists, data engineers, and also UX UI designers to bring this together. Hopefully, well, by next year, I've kind of been inviting myself here. We'll get to present something from our startup together with UNN and University of Tromsø, where we're working on using electronic health record data to predict infections in surgical patients. So that was it.
Thank you, Bart. We have time for one short question before the next presentation. Wonderful. And that is, what is your experience with data sharing between medical companies? Short answer.
Yeah, it's been complicated. I think we made the mistake of starting a company right after the GDPR got launched. But if you really look at solutions like federated learning, keeping the data where it is, I think you're safeguarding the interests of the patient and society, but also filling the obligation to actually get these kind of tools out there and develop them. So it's really looking at a technical solution in safeguarding our basic rights, but also our basic rights to a better healthcare. And I think that's a good joint effort, and I see a lot of energy, positive energy now going into that. So yeah. Thank you.
I'll just inform that Bart will be present during the digital coffee break. So if you have more questions or things you would want to discuss, you just need to make that avatar. Moving on to Cristina Soguero Ruiz. She received her PhD degree in machine learning with applications in healthcare in 2015 and has been a very active researcher within this field. She's a long-time collaborator with UN and UIT and is quite a familiar face here in Tromsø. Her current research interests include statistical learning theory, which of course warms my statistical heart. But now she will present an AI-derived early warning solution. Please, Cristina.
Hi, thank you so much. I'm going to share my screen. Let me check it. Can you see it properly?
We can see you.
Okay. So let me check it again.
Oh, we can see your screen.
Okay, perfect. But it's not in presentation mode. We were having problems when checking it. Let me do it again. And now, okay. Now, yes, perfect. Okay, so thank you so much to the organizer and for this conference. Today, I'm going to talk about data-driven decision-making for early warning of postoperative complication and adverse events. As explained, my name is Cristina Soguero and I'm an associate professor at Rey Juan Carlos University. And just before starting my talk, I would like to say thank you to the UIT Machine Learning Group for all the nice discussions, and especially to Robert Jensen for his support during my, since I started my research career, and also to Caribbean for the nice discussion during his PhD and also after that. So thank you so much. Also, I would like to thank you to Steinolaf and Ula and Arthur, because since then, basically this work and all the presentation I'm going to give today couldn't be possible. They share data and they provide us with great research questions. Some of them are in this slide. Today, we are going to talk about early detection of anastomosis leakage and prediction of surgical site infections. And all these problems has been done in collaboration with the machine learning groups. And also, as I said before, using data from the gastrosurgical and gastromedical department at a university hospital of Norway. But before starting, I'm going to present the data we are using. This is electronic health records data and can be categorized in different sources. For example, diagnosis and drugs codes, FRITES, and blood samples. And as said by the previous speakers, there are many challenges. Sometimes people believe that we are argue compared with using data in other fields, but I strongly feel that there are many challenges. We have to deal with scarce data, temporal data, high dimensional data. So many challenges that make more difficult the research. So yes, I'm going to show you a brief sample about the data we are using. For example, in this slide, we can see the main diagnosis and secondary diagnosis and procedure codes. Also, blood tests, we using them in several studies. As you can see here, sometimes we are able, or we are dealing with codes, with numbers, with tests, with some symbols, which makes us thinking that a preprocessing state is needed to have quality data. Also, we were analyzing a clinical narrative, and as you can see, there are many document types. I just going to show you some examples to see that some of them are completely unstructured, as for example, the jar note, and some of them can be semi-structured. There are some hidden that helps to understand a little bit better, or to easily analyze the data. And also from narrative clinic data, we extracted physiological variables such as body temperature, blood pressure, or heart pulse. And all this information was extracted from the nurse's notes. I don't want to spend more time in showing the challenges of the data, and I prefer to move to some research questions. And today I'm going to start showing some studies we done in the early detection of anastomosis leakage. In this study, we were dealing, the goal was when a patient have a tumor, the tumor is extracted, and sometimes the joint is not done properly. So then the anastomosis happens, and this can cause a lot of problems for the patients. So in this study, we were analyzing clinical narrative from 2004 until 2012 from around 400 patients. So using data from the electronic health records, we analyzed the clinical narrative, and we did something simple. We extract words, and after removing lowercase, numbers, some grammatical errors, we ended up in a bank of words model. And the idea was first do feature selection to see which words were more relevant for this study, and then we use support vector machine to be able to classify aware patients. Also, from a clinical point of view, it is really important to know if we were able to support decision-making up to the day of the surgery, or if taking into consideration more data, the results could improve. And of course, as you can see here in this table, when we are considering more data, better performance are obtained. But even just considering data up to the day of the surgery, we can say that the results were good enough. Also, I would like to emphasize here that after discussing with clinicians, some of the words we selected were really relevant for them. For example, air is an indication that the patient are going to have some problems related to anastomosis leakage. So we were happy with this study, and then we decided to see if adding more heterogeneous data sources, the results could improve. So here, a part of using free test clinical narrative, we decided to also use data from blood tests as well as data from vital signs. And using all these sources, we wanted to predict anastomosis leakage. In this figure, we can see that using unstructured data provides better result than using structured data such as blood tests or vital signs. However, we can conclude that when we consider all data sources together, as you can see in this figure, the results obtained were better than using each data individually. So the second research question I wanted to share with you today was the prediction of surgical site infection. This is a really important problem after surgery, and we want to provide some knowledge to clinicians. Here, I'm going to focus more on the methodological approach we will follow to deal with this problem. Again, we were using data from the University Hospital of Norway, and we have more or less 3,000 patients. Here, we were extracting blood tests from 2004 until 2012, and one of the challenges we had in this database is that it's really sparse. So the first approach we considered was imputation. So we checked different imputation approaches, and we ended up with the relevance of this blood test to predict surgical site infection. So in this slide, we are able to see that there are two figures, A and B, and we can see that different imputation approaches can provide us with different relevance. So this let us thinking more, and we decided to move a little bit from imputation, and we decided to move to something more stronger, let's say, okay, not only realize on imputation, if not doing something else. And after taking this into consideration, we decided to create some handcraft features, and we did this work in collaboration with the University of Maribor. And the idea here was to maximize interpretability as well as cost effectiveness. So basically, we have the same data, blood tests, and the same number of patients. And in this study, we decided to create some statistics in different temporal windows, short, medium, and long. And the idea, as I said before, is trying to use a linear model to have to provide a physician with interpretability, and also add prior knowledge of predictors based on the prices of these blood tests. So here in this table, we can see the results. We are able to see that in general, medium temporal windows, or statistic obtained from a medium temporal windows, were the ones which provide more knowledge to interpretability of this problem. Sorry. But still, we are not dealing with time. So we have time, and on the first problem, we just concatenated, and in this study, we decided to extract some statistics. But we believe that keeping the temporal structure can provide us with more knowledge and with improve the system accuracy. So in collaboration with the IE2 University, we work on a method called time series cluster kernel for learning similarity between multivariate time series with missing data. So here we can see that we have different blood tests, and we have time, and with random initialization, and with different number of Gaussian mixture model, and considering an ensemble approach, we were able to find local and global patterns to build the kernel, which we can use it for classification, clustering on, or this dimensionality reduction. So here I want to show the results we were we obtained using this methodology. On the one hand, we were using it for classification, and here we can see that as more days are considered, better results are obtained, both in training and of course in test. And also we were able to conclude that using spectral clustering, we were able to distinguish between infected and not infected patients with, let's say, in a good way. So we are now closing to using the temporal structure of the data and see the potential of this data. So taking that into account, we decided to move a little bit to deep learning, and specifically we were using recurrent neural networks. In this study, we were using vanilla RNN and also gate recurrent unit with decay and also without decay. And just briefly, the idea I want to share with you is that including the temporal aspect is we can obtain good performance. And also we are able to get visualization results using PCA, for example. We are also able, as we did it using TCK, of separated in some way infected from not infected patients. However, using vanilla RNN, well, results, as you can see here, were not so good. So yeah, we can say that, or we can conclude that using this data and using black tests and including the temporal aspect, we are able to predict surgical site infection properly. So just since I don't have too much time, I would like to show you a little bit the ongoing work. We are working right now using basically the same methodology I was explaining during my presentation. Right now, I'm going to talk about multi-drug resistant prediction, and in this case, I'm going to use data from the University Hospital of Fuenlabrada. As you probably know, there is a great debate about the end of antibiotics. A lot of people are becoming infected with bacteria, and they are resistant to antibiotics. So basically, we want to see if using antibiotics for more than 6,000 patients from 2004 until 2020 in the ICU, and analyzing this multivariate time series, we were able to create a kernel that we this kernel for visualization purposes, clustering, and classification. Just briefly, we can see that using visualization, we ended up getting a group of patients which acquired the multi-drug resistant during the first 48 hours. And this is really great because the chief of the ICU always tells us that if the resistance is acquired in that time windows, then the patient came with the resistance, and it was not this not occurred in the ICU. So also, if we can do some dimensionality reduction, as you can see here, again, there are several groups which are far away from the others, and also we can use on the top of that classification. And as you can see here, results are also promising. So basically, using the same methodology we were using for surgical site infection, we can say that we are on the way to predict antimicrobial resistance in the ICU properly. So just also mention that right now we are working in collaboration with the Norwegian Center for Health Research and with the UIT in a 2020 project called Watching the Risk Factors, Artificial Intelligence and the Prevention of Chronic Conditions. This project we are let's say, started working on it, so I don't want to show, or I cannot show still any results, but it will be great to give you, I hope soon, results about this project. And also I want to take the opportunity to say that there are some PhD positions available at Juan Carlos University just to work on data-driven decision-making models for extracting knowledge from electronic health records. So if you are interested, please, there you can find my email. So write to me and I can give you more detail. So yeah, thank you so much for your attention. I'm using this slide for several years now, because although we are far away in distance, I will say that in research we are closer. So thank you so much, and yeah, thank you.
Thank you, Christina. So Christina will also be joining the virtual room for the virtual coffee breaks. So all questions for her can be directed there. So we will now have a break until 10:45 sharp. We're working on the bit blurriness on the screen back here. Try to solve that during the break. So if you want to go into the virtual coffee room, just click the link on the conference website. And if you prefer to have your coffee here, just remember to spread out and use the alcohol for your hands. Thank you. We start again 10:45 sharp.